The sun is such an essential part of our life on Earth and our day-to-day lives that it is easy to take it for granted. But the sun is much more than a source of light and warmth. It is complex and dynamic and part of an amazing universe of stars, planets, moons, and mystery. Here are some interesting facts about the sun. The sun is 93 million miles from Earth. It is composed of 74% hydrogen, 25% helium, and 1% other elements. The average temperature on the surface of the sun is 5,800 degrees Kelvin. And at the center of the sun, temperatures average 15.5 million degrees Kelvin. Just like a planet rotates on an axis, so does the sun. But unlike solid spinning objects, the entire sun doesn't rotate at the same speed, because the sun is not solid, but is instead a giant ball of gas and plasma. Different parts of the sun spin at different rates. The rotational period is 25 days at the center and 35 days at the poles. And the sun is 25,000 light years from the center of the Milky Way galaxy. Each part of the sun plays a special role in how it creates light and heat. There are three main parts of the sun: the core, the radiative zone, and the convective zone. The sun is surrounded by an atmosphere which itself has three separate parts: the photosphere, chromosphere, and the corona. Let's begin at the center of it all, the sun's core. Deep in the middle of the sun, there is intense pressure as gravity pulls all the mass of the sun inward to the core. When measured from the very center, the sun's core extends out 1/4 of the sun's total radius. The pressure in here is strong enough to force two atoms of hydrogen to come together to create helium-4 and energy. This reaction is called nuclear fusion. Think of it like this. The sun burns hydrogen in a nuclear furnace, creating helium. Hydrogen is the fuel. The change from hydrogen to helium gives off energy, and the resulting helium is the ashes. This process has been going on in the sun for about 5 billion years, and scientists have calculated that there is enough hydrogen up there to keep the sun going for about 5 billion more. Moving out from the core, we find the radiative zone, where the sun transfers its energy out into space. This zone is about 55% of the sun's radius from the core. The energy made in the core is in the form of gamma rays when it first begins its move outward. In the radiative zone, this energy is changed into photons. They move at the speed of light, but constantly bump into so many other particles along the way that it takes hundreds of thousands of years for them to get through. Think of a pinball machine and all of those bumpers and flippers, and then you multiply that by 1 billion, and you get the idea. The average temperature in the radiative zone is 4 million degrees Kelvin. The photon's next stop is the convective zone, where the sun's energy continues outward toward the surface. The temperature in the convective zone falls to about 2 million degrees Kelvin, and here atoms can maintain their electrons. That intense heat in the core makes it easier for the electrons to be stripped away from the atoms. Atoms with electrons can absorb and give off radiation, and that process makes the convective zone appear foggy. Check out this outer shell of the sun. Here, hotter gas coming from the radiative zone rises into the convective zone. The gas then cools, causing it to sink back down to the radiative zone. The gas gets reheated again, and the process starts all over. This swirling action in the foggy convective zone makes the sun's surface appear bubbly, like boiling syrup. Officially, it's called granulation, but don't be misled by the name. Granules, when we're talking about the sun, are more than 600 miles across. Supergranules are even larger, about 28,000 miles across. Those atoms that escape make it into the sun's atmosphere. The first layer of the atmosphere is called the photosphere. It's a very thin layer compared to the rest of the sun, but it's the only part of the sun that we can see from Earth. The photosphere is where the light is sent out. It's anywhere from 180 to 240 miles deep, and averages 5,800 degrees Kelvin, a far cry from the heat of the sun's interior. Moving outward, the temperature continues to drop, and the gases do not give off as much light energy. This causes the outer edge of the photosphere to appear dark, giving us the impression from Earth that the sun has a crisp edge. Things are very different in the next layer, the chromosphere. Instead of temperatures falling as the distance from the sun's core increases, the opposite is true. The chromosphere extends from the photosphere about 1,200 miles, and as we move from the top edge of the photosphere outward, the temperature rises from 4,500 degrees Kelvin to about 10,000 degrees Kelvin. Normally, the chromosphere cannot be seen by the naked eye because the light from the photosphere overpowers it. Yet during a solar eclipse, that narrow red band around the sun, it's the chromosphere. Its edge is irregularly shaped and made of spicules, or small eruptions that eject material into the corona at high speeds. The corona is the collection of gases immediately around the sun. It is extremely hot, with temperatures reaching to 2 million degrees Kelvin. You may have seen the corona during a solar eclipse. Just like the chromosphere, this is the only way to see the corona with the naked eye. Here you notice bright areas and dark spots. The brighter the area, the hotter the temperature. The dark areas are called coronal holes, and they're thought to be where particles of the solar wind escape. The solar wind is the constant flow of charged particles coming from the sun in all directions. This energy reaches the Earth, where it warms the planet, drives our weather, and provides energy for life. Fusion is the joining of two atomic nuclei. This requires extremely high energy in order to overcome the electrical repulsion between two positively charged nuclei so they can get close enough together to have the strong nuclear force bind them together. Think of two magnets pushing away from each other when both positive ends are facing one another. Nuclear fusion in the sun happens in several steps. Most of the energy created by the sun is generated during a sequence of reactions where hydrogen burns into helium. This is called the proton-proton reaction. It all starts in the core, where, remember, temperatures are somewhere in the neighborhood of 15 million degrees Kelvin, and density is 100 times greater than the density of water on Earth. This intense environment makes it possible to strip hydrogen of its electrons, creating this flowing mass of free electrons, protons, and the nuclei of the hydrogen. So step 1, strip hydrogen of its electrons. Step 2, extreme heat causes the hydrogen ions to collide with enough force to bind them together. Step 3, the heat also causes other particles to collide, releasing gamma rays, which are high-energy photons. Step 4, more collisions release more photons, which eventually work their way through all the sun's layers and reach the Earth, traveling on the solar wind. This energy can be harnessed and used to make electricity. No need to burn fossil fuels like coal, oil, or natural gas. The sun has it down to a science.